good morning, wherever you are. This is Rajaram. I am a senior manager at Alcatel-Lucent in New Jersey, USA. However, I am right now in Bangalore, India, and this webinar is coming to you from Bangalore, so where it is 3:30 p.m. in the afternoon. Today's topic is thermal design of electronic equipment for reliability and performance. And what I'm going to do today is give you a fairly broad overview of this subject, give you an idea of its importance as well as some examples. It's a very broad subject, so in a matter of an hour or hour and 15 minutes, I can't go into great depth on all the various design aspects, but what I would like to do is give you a good feel for what the issues are, why we address this, etc. Okay? And I think what we will do is, in the interest of time, let's reserve the questions to the end of the seminar. Okay? So I'm now moving on to the next slide. And first of all, the obvious question that comes to mind is, why are we concerned with the thermal design of electronic equipment at all? And the very fundamental reason and the answer is that in order to have very reliable product in the field, in order to minimize risk of failure, thermal design becomes the most important aspect of electronic design, one of the most important. So from that definition, you can see thermal design and reliability engineering are very closely related. So in most of the communications equipment, there is a requirement for defining what is called a high availability system, HA. So what does this mean? A high availability system usually is referred to as 5 nines reliability, and what that means is that it is 99.999% reliable. So in real world, what that translates to is that any equipment that is designed cannot have a failure of more than 5 minutes for a whole year. So you can have one failure for 5 minutes, or you can have 3 failures in a year, but the total failure time for all of these failures cannot exceed 5 minutes. So this is what and how telecommunication equipment is designed. And if we don't do this, we cannot sell the equipment because it's a requirement. So one of the important aspects of reaching this goal is to have very good thermal design. And thermal engineers therefore get involved with reliability engineering, and so I want to emphasize to you that when you think of thermal design or thermal engineering of electronics, you also need to be thinking in parallel of reliability engineering. Why is that? Because ironically, while the products are all fancy software and hardware products, most of the failures tend to be mechanical in nature. And we know that from our experience over the last 30 to 40 years. So thermal design and temperature control become most of the important parts of design. And these are going to continuously remain a challenge because the power levels are just continuously going up, as we should see shortly. Now, the next question then is, if you said that temperature is important from a reliability perspective, what is the impact of temperature and why is it impacting reliability? The reason for that is, with experience in the field over the last 40 years or more, we know that temperature accelerates all of these failure mechanisms that I've listed here. I'm not going to go through each one of those, but just to give you an idea that all of these failures that we see in the field, which have been very thoroughly analyzed and understood, tend to be driven by temperature. So in order to prevent these failures, we have to keep temperatures under control, and this is becoming a big challenge because the power levels are going up and we are constantly being pushed as the limits are of the temperature and the power are going up, and in order to reduce the failure in the field, you've got to make sure that none of these happen. Okay? Just to give you an example, here are 2 failures that you see inside a device. After it fails, if you look at it, at the left is a electromicrograph of an electromigration failure, And on the right-hand side is actually a failure of a silicon device inside. You can see a crack running through the device, and this crack originated at this point that I'm pointing out to you at the base of the silicon, and because of thermal stressing, it propagates and then leads to failure. So these are just two examples giving you an idea that temperature indeed is driving failures in electronics. Okay, so the reason this becomes very critical is that because it has very big impact in terms of the business drivers and field costs. So remember, I talked to you about 5 nines reliability. Let me just give you an idea of what this translates to from a business perspective, and what does a field failure cost us. Let's take the simple example of a mobile phone. If a mobile phone is not designed and built properly and it fails in the field during the warranty period, typically the cost of analyzing or fixing or replacing the phone can be an average of about $100. So let's say you, for every 1 million phones, you've got 1% of those failures. 1% doesn't seem like a big number. But if you have 1% of those phones failing in the field, for every million phone, the cost of that failure is $1 million. So for instance, if you take mobile phones, those are sold usually in the tens of millions. So typically when we have failures, and we're talking about very small failure rates, the cost of failure for fixing and warranty and repairs can turn out to be tens of millions of dollars. And typically for more complex systems, the cost of fixing a circuit board or a failure in the field can actually vary anywhere from $3,000 to thousands of dollars depending on the complexity. So the thing to keep in mind is that ultimately if we do not build reliable systems, we are going to end up with penalties, and we may have legal penalties as well as penalties for repaying back or providing new devices. So good thermal design is one of the most important things to mitigate field failures. Okay, so as most of you are well aware, the device power levels are continuously going up. On the left-hand side are the power levels shown for notebook computers, and this is the CPU. And for the high end, you can see the power level started around 30 watts and is going up all the way to about 60 watts. If you look at network communication equipment, the power levels today exceed devices that are exceeding in more than 100 watts of power today. So I'll show you some examples of that. So what the trend that you see here is a continuously increasing power dissipation. So what this translates to as far as our design is concerned is that the thermal designs are becoming more and more of a challenge as these power levels are going up. Okay, and this is actual data from the products that are out there. What is driving these thermal dissipations? A lot of it is driven by the device technologies. Most of you have probably heard of something called Moore's Law that states that the number of transistors sort of doubles every 18 months or so. So that's what you see in these graphs. What you see in this graph here on the left-hand side is the number of transistors, and as you can see, as we went from, say, just take 1990 to 2010, you can see the tremendous increase, and it's a continuous increase all the way from 1970 to today, and it's going to happen continuously. So if you look at the number of transistors, millions per centimeter squared, again, that is continuously increasing. Now, the reason that is happening is because the size of these transistors are becoming smaller. So you can pack more and more, and on top of that, the clock frequency of these devices are going up. And you're very familiar with laptops and PCs, where you buy a device today for 2 gigahertz, in 3 months it's 2.5 gigahertz, etc. The higher the frequency, the higher the power dissipation. So you combine the number of transistors and the higher frequencies, the product of the two means an ever-increasing heat dissipation. And this is what is driving those devices. And as we are putting more performance into these notebooks, into the laptops and other devices, the power is continuously going up. Okay, so this roadmap trend that I've shown you is the primary driver as to why power is continuously increasing. Okay, all right. Now, if you look at IT data centers, the handbook, they give you the power dissipation. This is the footprint. That's the watts per meter squared over the years. And what I've plotted on that is actual products from our company. And as you can see, we actually follow, and the power levels have reached the maximum levels that are predicted here, and we're already at these levels. So once again, this is a proof that indeed the power levels are going up, and this is causing a lot of issues with thermal design of electronic products. Okay, and these circles that you see here are based upon actual products that have been plotted onto the chart provided by ASHRAE. All right, so what are the challenges that we face? I just want to show you some examples of actual devices inside and what some of the power levels are. I talked to you about dissipating close to 100 watts. This is actually a power amplifier which is used in wireless communication networks. And this is a cross-section of a device. Within that device, actually you see these 3 green fingers. Each of these fingers, the size is 810 by 6,246 microns. And on that, you've got 64 active cells as shown here. These are the junctions of the transistor where the transistors are switching back and forth and dissipating the power. Now, each one of those may be dissipating a small amount, but the total power from all of these being dissipated is 85 watts. If I looked at the area or the density of heat on this, based on the size of the die and the power density is 1,700 watts per centimeter squared. So just imagine that. It's like putting a toaster oven on top of this small surface. This is the high heat density that we are dealing with today inside those devices. Now, we do this through experiments, we do through modeling, and this is an example of a finite element model using 18,000 nodes and so 13,000 volume. And these red dots that you see are actually temperature. This is the hottest spot where the device is dissipating. And then from that we calculate the temperature of those hot spots. Those are called the junction. The junction is where the transistor power is being dissipated. Then we measure the temperature of the case. That is where it is mounted onto a heat sink. And we define a thermal resistance shown by these numbers. And as you can see, for 80 to 85 watts, depending upon the sink temperature, that is the mounting surface temperature, the junction of the device can reach anywhere from 158 degrees that is shown here all the way up to 175 degrees. So this is above the limit at which these devices can function. So this is just to give you an idea that the numbers that we are talking about are real. So the power levels and the densities are extremely high. So what does this mean in terms of electronics? So when we have an actual board or a design, typically on a microwave board, you will find 2 or 3 of these devices sitting on a board that is shown here. And this is pictorially showing the temperature. This is the hot spot where the device is, and then around it there's a spreading of the heat. And what we've done here is we've actually opened the device, removed the cap, and we've measured the temperatures using an infrared. So this particular device has 4 fingers dissipating heat, and that's these 4 fingers of hot red that you see. And this one has a single finger that's dissipating heat, and that is, when you take the infrared picture, this is a single picture of it. But here's the interesting thing. Look at what is happening on the chart over here. This particular device here is actually, there are 4 devices here, and the thermal resistance of that is only 4.5. Whereas this particular one is a single device, its thermal resistance is actually 7.8 to 8. The reason for that is because of spreading resistance. You, as thermal engineers, you would have studied about thermal resistance and thermal spreading resistance. So when the heat is very concentrated at a single point, it has a higher resistance because of the spreading or constriction resistance. So this is just to show you an idea. So these are all factors that we take into account when we design products, looking at how we can minimize temperature. We distribute the heat, we minimize the resistance. These are all things that we look at from a both measurement and modeling perspective. But I just want to give you an idea of real-world design parameters that we deal with. Okay, and this is a real design where the devices are each dissipating about 80 watts. And basically what the spreading resistance does is leads to these device hotspots. And these device hotspots are what we are trying to cool and keep under control. All right, so what are the temperature effects of electronics? Typically, of course, we are familiar with the ideal temperature for man and machine. Typically, an electronics will be sitting in an environment in the 50 to 55 degrees C ambient. So if you look at the case of that package, normally for commercial components, we would not allow that to exceed 75. The case limit for many devices usually can be 85 to 95, where it's higher grade devices. The board on which it sits, usually that is limited to 105 degrees C. And inside the device, the junction that we are talking about, typically for plastic packages and commercial equipment for silicon, we will not exceed 125 degrees C. Typically, 125 degrees C is a maximum that we will allow. So most of our designs, we will actually stay about 10 degrees cooler than that. So the limit is 125. Now when you go to microwave and wireless devices, gallium arsenide, this is silicon 125. Gallium arsenide, which is used in wireless applications, typically we will go in the range of 150 to 175, but we will definitely not exceed 175, and typically we will stay below 150. So the point that I want to make to you is, regardless of how much power we put into these devices, how much heat we dissipate, we are limited by this number of 125 degrees C or 150 degrees C as a maximum temperature inside that junction of that transistor. We cannot exceed this temperature. If the temperature exceeds this, the device will most certainly fail. So I want you to keep that in mind, because what I want to show you on the next chart is some of the constraints we have to live with, and to see how severe these are inside electronics. Now, just to give you an idea of the challenge that we face, what is shown here is the temperature on the x-axis in degree K for various natural and man-made designs and phenomena, and the heat fluxes or heat density in watts per centimeter squared. For instance, if you look at on a bright day, let's say in Bangalore, where you have solar heating, typically around the equator, southern part of India, the solar heat flux is roughly 0.7 to 1 watts per meter squared, 700 to 1000 watts per meter squared. So now if you, let's say you put a metal plate sitting there to equilibrate, typically you will find that may reach anywhere in the range of about, could be 70 to 100 degrees C. That's like, in the range of 350 to 400 K. Now, you can look at various phenomena here, and the thing, for instance, if you look at a satellite or a rocket motor case, or maybe better still, this re-entry of a satellite orbiting the Earth. When it re-enters the Earth's atmosphere, it's traveling around 25,000 miles an hour. Because of frictional heating, the surface of that satellite or rocket actually reaches somewhere around 1700 degrees K, which can be in the range of 1500 to 1600 degrees Celsius. And the heat loading on that is roughly about 50 watts per centimeter squared. But those rockets are designed, the surfaces are designed for reaching a temperature of 1600 degrees C. Now, ultimately, if you look at the surface of the sun, the surface temperature of the sun is about 600 degrees K, and on the sun's surface, the heat fluxes are typically in the range of about, say, 10,000 watts per centimeter squared, somewhere in the 5 to 10,000. However, let's look at our electronics. You remember the heat loading I showed you in the electronics on the device before? This particular one, 1700 watts per square centimeter. So here we are with a device that has a heat loading at its junction in the range of 1700 watts per centimeter squared, 2000 watts per centimeter squared. And what we are telling that transistor is you cannot exceed a temperature of 125 to 150 K. So as far as electronics is concerned, this x-axis is fixed. You have no luxury to move outside of, no freedom to move outside of this temperature range. However, this axis is going up. So this is the challenge we face. So it's kind of interesting to realize that we're reaching densities right now which are like the surface of the sun. However, the surface of the sun is 6,000 degrees K, but we are not able to allow the device to function. The device will not function, or it'll fail if it goes above 150. So that's the challenge that we face. Just to put things in perspective for you as to how important this is from the perspective of a thermal design. Okay? All right. Before we go into the actual thermal design, I want to give you some very fundamental definitions of reliability itself, because as I told you before, in order to do thermal design, you also need to have a good understanding of reliability. Some very basic definitions I'm going to give you. First of all, reliability is not something that you measure. The way we calculate reliability for a product is actually by looking at failures. We power products and drive them to failure, and we actually determine through data what the rate of failure is, that with time. And then we say reliability is just 1 minus the probability of failure. This is a probabilistic problem. It's a statistical problem. So it's a roundabout way that we measure reliability. We really only measure failure, and we say reliability is just 1 minus failure. When I say reliability, I mean this is a probability function. That's why it's 1 minus f of t. Okay? Those are the definitions that I've shown here. In practice, what we do is we actually measure what is called lambda. This should be lambda of t. Lambda is what is called the failure rate. And then you can mathematically show that reliability is nothing but this exponential integral of 0 to t of this function. Now notice that if lambda is complicated, this expression can be complicated. However, fortunately for us, for electronic devices in their useful life, lambda tends to be a constant. So when lambda is a constant, this becomes a very simple integral, and r of t is nothing exponential of minus lambda t. So lambda is called the instantaneous failure rate, and we measure this experimentally. So the thing that I want you to remember is that in order to predict reliability, you must precipitate failures. We drive products to failure, and we determine lambda. Once we know lambda, we calculate r. So just believe me when I say lambda is constant, and I'll show you later on why that is so. So here's another interesting paradox in terms of reliability. If you don't have failures, you cannot predict reliability. It's a paradox. So if you don't have products that fail in the lab when you test, that we don't drive to failure, then you really don't know much about the reliability of the product. Something to think about, okay? All right, so what is the impact of temperature on failures? So we all know from our basic classes and fundamental class in chemistry or chemical reactions that chemical reaction can be written by a relationship which is exponential in nature called the Arrhenius relationship, which says that it is dependent upon a parameter e to the power of EA minus EA over KT, where EA is called the activation energy, K is the Boltzmann constant, and T is the absolute temperature. Now, the time to failure for electronic devices from this, you can show that is related to the same parameters as shown in this expression. So what this is telling you is that the higher the temperature, the faster the time to failure. So that's the dependence of temperature and failure. So the thing that I want you to remember is temperature has an exponential impact on the driving products to failure. So EA is called activation energy, and EA is just a manifestation of how important temperature is to drive products to failure. Typically for most electronics, EA will be 0.5 to 1 electron volts for silicon, and it's 1.5 to 1.6 for gallium arsenide. And K, of course, is Boltzmann constant. So the thing to remember is that the higher the activation energy, the more important temperature is driving failure. So activation energies are usually determined by experimental data, and it is very well understood and tabulated for all the failure modes that I showed you before. Each one has its own activation energy. The combined effect is this number that we see over here. All right? So that is how important temperature is. It has an exponential relationship. So when we have failures in electronics, it's not just temperature that drives things to failure. There's a whole bunch of other stresses that drive things to failure. Temperature is just one of them. In addition, the stresses are voltage, there's humidity, there's temperature cycling, vibration, electrostatic. All of these have their own acceleration factors. And for temperature, it is defined by this number. For voltage, it is defined by this expression. And for humidity, it is defined by this expression. But what I want you to take away from this is that when you have multiple stresses, the total acceleration is the product of all the stresses. And notice that all of these have an exponential impact on driving things to failure. So it's a very, very drastic impact that temperature has on driving things to failure. So that is the critical message from this chart. I told you about these activation energies for various failure mechanisms. So these are all things that have been studied very well, and you can see this is the effect of temperature, this is the effect of voltage, and the activation energies and constants are all very well understood, and those are what I mentioned earlier to you in that combined number. All right. I remember I told you we determine activation energy from failure data. So here is actually, I'm showing you a plot of the failure data for a power amplifier. This is a gallium arsenide device. Remember, I told you normally we will not in a design exceed 150 to 175 as a design junction temperature. But when we do the testing to drive this to failure to look at device behavior and determine its reliability, we actually test these junctions at very high temperatures. And you can see we've tested all the way from 260, 240, 275. And then the way this is done is you may power up about 60 of these devices and subject them to these temperatures that are shown in this table. And you look at how many hours it takes for median life of, that means 50% of the product will fail. And these are the number of hours. And then you plot this curve on a log scale over 1 over T. And then from this expression, you can back calculate what EA is. And from this test data, notice that from the data, we see that the activation energy for gallium arsenide is 1.5. And this is what I mentioned to you. So this is how it is done for devices. So this is all very well understood. Therefore, we know how these will behave with temperature, and therefore we know how we can predict what the field failure is going to be if we exceed the temperatures, or how long it will work in the field when we move away from the maximum temperatures. So a lot of this is empirical. It's based on statistics. As you can see, we collect the data and then we plot a best fit curve over there. And so this is based on a lot of statistics and empirical data analysis. All right. So I told you about the exponential nature of temperature driving to failure. So what this chart is, what it tells you is, I'll just take any, suppose there's a product sitting at relative to, suppose the product is to operate at a 60 degrees C ambient temperature. Instead, suppose I operate this product at, I'm just going to say 125 degrees C ambient. What this table is telling me is that if my activation energy is 1 electron volt, 1200 hours of operation at 125 degrees C is equivalent to 40 years of operation at 60 degrees C. So you see, what I want you to understand is how important temperature is to shorten the life or drive things to failure. So what we are saying is that it's not as though when you get to 125, all the devices are going to fail. But what this is saying is that the probability that you will have a high failure rate is very high, and 1200 hours of operation at this 125 degrees C is the same as operating for 40 years at 60 degrees C. So what this is saying is keep your temperatures low, keep the devices running efficiently and cool. You will extend its life in a very big way in an exponential manner. So that's what this table is telling you. Okay, so one more thing before we get into actual thermal design or heat transfer of electronics. Remember I told you we measure lambda, the failure rate of a product. Typically what is done is that electronics are, you take a sample of product which may be, let's take about 100 devices, and you power them up and at a high temperature. And then what you do is you monitor them over time and you measure the number of failures. Let's say that, so typically what will happen is you will find that very early on there will be a relatively high failure rate. This is failure per unit time. That means if I started with 100 and over a period of 10 hours, let's say 2 fail, then the failure rate is 2 over 100 units per hour. And then I look at the remaining 98, and then over a period of next 10 hours, maybe 1 failed. It's 1 over 98. So that's what this number is. It's the failure rate per unit time. So if I were to plot the results, if I were to take thousands of these units and test them, I will find that initially I'll have a high failure rate. Very rapidly that will go down, and I will reach a point at which the failure rate will no longer change. It will remain fairly low and constant. And then over an extended period of time, what will happen is once again the failure rate will go up, and it will go up in an exponential increasing manner. This is exponentially decreasing, this is constant, and this is exponentially increasing. So this curve, as you can see, has 3 distinct regions. This early region is called early failure or infant mortality. And the major cause of failure in this infant mortality is usually manufacturing defect, component defects from our other vendors. Then once you weed those out, you reach a very, very low failure rate, and the failure here is normally due to design failures. And over an extended period of time, this could be, in real world, it can be 10 years, 15 years, 20 years. It starts to, what happens is there is, and this is called steady state in this constant failure. Later on, what happens is failure rate starts to increase, because what happens is devices literally begin to wear out. You'll find oxides inside, you'll find corrosion, you'll find fatigue, and this region is called wear out. It's like old age. So this is called wear out. Now, because of the shape of the curve, it is called the bathtub curve, because this curve looks like a bathtub. And all electronics, single devices to boards to systems, have this very unique characteristic. So now, when we send the product out, we always weed out this failure, and this steady state period from the time of end of failure to where wear out begins is called the useful life of the period of the product. And remember, I said earlier on that during the useful life of the product, lambda is a constant, and that's where this comes from this curve. Now, when we design a product, let's say you're designing a PC. to last for 10 years. Typically, we want to design a product so that this wear-out period is very, very far away from the useful life. So if you keep a mobile phone for 3 years and you're changing mobile phones for 3 years, we will typically design a mobile phone for anywhere from 10 to 15 years. Similarly, for a PC, we will design for 15 years. A telecom equipment, we will design with a life of at least 25 years. It's not that it does not mean that we're going to keep the product for 15 years or 25 years. What it means is that we want to ensure very high reliability so that this point is never close to when the product will be not used again. The reason for that is if this failure happens, this is an exponential big failure rate, and we do not want this to happen during the user. This is where these two are the cause of all those warranty failures I talked about, which can cause losses in the tens of millions of dollars. So the reason we do thermal design is to ensure that we say we want a product for 25 years, we want to make sure that the product is thermally designed so that it can last 25 years at least, and then the product may only live for 5 years or may only be used for 10 years, but we want to design it in such a way. That's from a mechanical engineering perspective. Those of you who are mechanical engineers, you remember this is the factor of safety. That's what it's all about, okay? Thermal design is ultimately minimizing risk, all right? Okay. So let me now switch gears and, get into actual thermal design. So that sort of I wanted to give you that fundamental grounding and understanding of why we do this, because I did not want this to be just a heat transfer analysis, okay? So that's the basis for why thermal design is important. Now, when you go into thermal design of the electronics itself, what is the nature of thermal design? If you are a mechanical engineer and a thermal design engineer, what are all the things that you have to understand and know to design products? What you will find is that thermal design in electronics turns out to be a multifaceted heat transfer subject. It actually invokes, depending upon the type of product you build, it invokes all of the areas that we typically study in heat transfer. Conduction, convection, and radiation, fluid flow and pressure drop, extended surfaces, which is heat sinks and fins, a lot of experimental work, data analysis is extremely important, as I pointed out to you earlier, numerical, computational fluid dynamics, CAD, heat exchanger design, heat pipes, fan selection, and acoustic noise control. You need to have some fundamentals of acoustics because noise control is becoming very important in electronics. Microchannel cooling, jet impingement, liquid cooling, boiling, thermoelectric refrigeration. So all of these things are important. Again, as you can see, depending upon the product, you will see many of these modes of heat transfer that are being utilized for design. Okay, this is just to give you a perspective. It's a very broad field. It touches upon many of the areas that we classically study in universities and schools. And the trick is really trying to make that gap between the analytical and the theoretical studies that we do in heat transfer and the actual design where things look very different. Okay, what I want to do is just take one example of that, just to show you of how we actually do design of equipment when we design products. So what I'm showing you here is a typical telecom product. It's a communication product. You can have these, each one is a shelf or a rack. In each of those racks, you will have a board. This board, each of these boards will have multiple devices, and each of those devices inside will have many power generating or transistors or areas. And normally in a system like this, I'm showing a system which uses fans. The fans will blow air in the channel between the boards. So essentially you have air flowing over these boards and cooling them. And then from these packages, you've got these leads. These leads can be of different materials, copper alloys, aluminum alloys, etc. And the heat from here is dissipated through the package, through the leads, into the board, and carried out by the air through convection. Now, if this is a product that is in space where this can be a solar wing, essentially you've got radiation. So this is a very typical product, and the way we do it is first we look at it from a system level. we do analysis at the global system level. We have all the information about the product. And then what we do is we determine the environment around each of those boards from a system analysis. Then we do a board level analysis. From that, we get information about temperature around the board, temperature on the packages, how much heat is dissipating by each package. Then what we do is we do detailed analysis and measurements around each device. And then we look into each of those from analysis and measurement. So that's the sort of hierarchical step that we normally do. We go from system to board to package, and then what we are trying to do is we are looking at the transistor temperature, which is the junction temperature, inside this device, inside this junction, and that must be below 125 or 150. That's the procedure that we follow. Okay? I want to show you some typical designs. This is actually a wireless enclosure. The PC board. Are we having any difficulty?
Yes, sir. You were offline for about 10 seconds. So.
Can you hear me now?
Yes, sir.
You can. Okay. All right. So this is has heat exchangers and fans. This one has no fans. It's sitting on the outside. It just uses big long fins for cooling, and it's sealed inside with some graphite pads to conduct heat from these devices onto the heat sinks and cooling. This is one design. Here is another design. Here is a board. This is called a conduction-cooled PCB. No air can go over these components. These components or devices are sitting on a metal-clad board. Heat dissipates into the board, and then it goes out into heat exchangers, and you can have liquid or air going through these heat exchanger fins carrying the heat away. This is called a conduction-cooled board, and this is typically used in avionics where they do not want humidity coming onto the systems. Another design is what is called a heat exchanger that is sandwiched with between boards or on a single board. This is the heat exchanger becomes part of the board, and here you can have air or you can have liquid cooling. So this is another design. So each one of these are different. When you go to these heat exchanger designs, you can carry a lot more heat. You can dissipate more heat when you do those. And now what we are doing is, and this is just, we build CAD models of those, and what I'm showing you here is the heat exchanger. Here is the board with all these devices in there, and then we do the finite element analysis, and we also do measurements through markups using the same heat loading. Now, here are different kinds of electronic products that are shown here. This one is just basic heat fins. This one has devices with copper plates, and inside these copper plates are heat pipes. And here is a design with heat pipes that are used to carry heat away from the hot spots onto a heat sink and move them away. And what you're seeing here is a heat pipe. Here are the hot devices. There's a heat pipe carrying the heat all the way down into the base of the heat sink and dissipating it out. So these are all various designs that we encounter, and these are all part of our products today. So again, as I pointed out to you, you've got to be able to work on these different areas of heat transfer or thermal design when you're designing electronic products. Here's actually a measurement inside a mobile phone, and as you can see, when you start talking on the phone, inside the phone, these devices run very hot. You can see the worst is the power amplifier. For those of you, if you talk for a very long time, and if you touch the phone at the top, that's where the power amplifier sits, you will notice that that is the hottest part of the phone. In this particular case, there was you can see the phone, the power amplifier on the phone is reaching 85 degrees to 90 degrees. And in fact, the users were complaining that it was heating their ears, and they were complaining of not being able to touch the surface. This was actually a problem because of poor thermal design, and this product was redesigned. I'm just showing you actual data from measurements inside this device. This is, you can see, this is the power amplifier, the hottest, and LCD is the display. The display also is running at 50 degrees C. Okay. All right. So we talked about this, the nature of thermal design. You have to, it's a multifaceted heat transfer subject. So why does what are some of the issues that we face in thermal design? First of all, as you all know, heat transfer is actually an empirical science. So a lot of it is based on data, a lot of it is based on predictions and measurements. And so actual accurate prediction within equipment becomes a very difficult task. Why is that? The reason for that is we've got complex geometries, you've got non-uniform component sizes and layouts. I showed you some of the pictures of the products. You can see nothing is uniform. In fact, there are very few equipment that are very uniform geometry. Some of those are communications equipment, like I showed you, sitting in racks with boards that are parallel to each other. Heat flow is never uniform. Flow distribution is not uniform. Measurements become a big challenge because you cannot reach the devices. You cannot reach into the junction of the transistor. So lots of uncertainties. On top of that, the power dissipations that the designers give you themselves may not be extremely accurate. So typically what we have done over the years is through experience, we've got a lot of rules of thumb that we design. We actually can do a lot of predictions, and we do minimum experimentation, but we certainly have to do experiments. So part of thermal design of electronics is always experiment. So there's no design that we send out without experimental testing and confirmation. So, but it's a complex subject. As much as the fundamentals are known, in practice it becomes complicated because of all these factors that I've shown you. Again, just showing you some examples. Here's an enclosed cabinet. This is very typical for electronics that are sitting outside. They are completely enclosed and sealed because you don't want dust, moisture. And what happens in there is you've got solar loading on top. This is the 700 to 1,000 watts per meter squared. Hot air keeps circulating inside. It cools at the external surfaces, comes down. And so we then can calculate all the temperatures inside the board, the case, the devices. We do CAD modeling and measurements to do this. So there are limits to what you can do with a completely sealed cabinet. Now, in the open cabinet, like the shelf I told you, there you're allowed to use fans to pump air continuously through. The problem is very similar, except that the fan can pump air, pick up heat, and go outside. And once again, we do the same things. We take the information that's provided, and then we calculate these parameters that are shown here. Then, what are the modes of heat transfer? As you can see, conduction is the primary mode, because inside I've shown you two different types of devices. Here the device is sitting at the bottom. Here the device is sitting at the top. From this hot spot shown in red, the chip as we call it, or the die, heat goes out through all of these materials that are connected to the package, out into the heat sink and out into the air. So the primary mode is conduction. And here's a finite element model of that. And here's actually the finite element model of a particular device that I showed you earlier. So we do finite element modeling at this level because it's all pure conduction. But at the surface, we have convection. So here is another package. Here is a chip sitting on a copper board. So what we do is to increase the amount of heat that we can go through in this board, which has glass and copper. We have drilled copper-plated holes. It behaves like thermal shunts. And then heat gets carried away by air flowing over this device. But then heat gets carried away by air flowing on the board. Heat goes from the device down into the board. And as you can see, as the velocity goes up, the thermal resistance goes down. So we do all these measurements through the So this is another example of actual design package. So this is primarily conduction convection. So what are some of the materials used in electronics and the thermal conductivities? And as you can see, varies all over the place. The plain glass epoxy copper board, very poor thermal conductivity, 0.3. When you add some copper in it, there's always copper in it because it has conducting planes and ground planes. It goes up to 10, and it can go as high as, say, 20. And these are the leads from the device. So these are all different compounds that are made of the package compound, and these are the frame that are made up the leads. So these are all the material properties that we deal with, and you can see it varies all over the place, from all the way from 1 watt per meter degree C all the way to 100 watt per meter degree C. Just to give you an idea that the kinds of materials and the thermal properties that are used. Now, the modes of heat transfer convection. As we pointed out, when the air flows or water flows in that heat exchanger, it is going to be primarily removing heat through heat transfer coefficient from convection. And so we calculate what that H is from what we know in heat transfer studies or measurements, and then we can calculate thermal resistances. Then you finally do have radiation as well. All external surfaces cool by radiation to the outside, and particularly in space electronics, all the heat that is dissipated that's out into outer space is all purely radiation. In those enclosed cabinets, the outside surfaces have radiation. So there is a radiation heat transfer coefficient like the convection heat transfer coefficient, and you will find that convection and radiation are equal partners when you do not have fans. So that is, any two surfaces we measure and calculate the radiation through the radiation heat transfer coefficient. And you can see here the radiation heat transfer coefficient in watts per meter degree C for various surface temperatures. And typically in electronics, we do not want the surface to, the ambient may be 50 degrees C, and the surface may be in the range of, say, 60 to 70 degrees C. You can see the number is of the order of about 6 to 8 watts per meter squared degree C. And if you do heat transfer coefficients for natural convection from flat plates, you will find that that number is roughly the same. That's why when you have radiation and no fans, you will find that radiation becomes a good contributor to heat dissipation. And finally, we do have another kind of resistance that we call the fluid resistance, and that is, as you know, when you have a heat exchanger or a box where water or air goes in, it picks up heat from the product and comes out, it increases in temperature. So what that means is it's as though there is a resistance, a thermal resistance, and that thermal resistance is defined by the mass of the flow, the velocity, and the area. So there are 4 kinds of resistances that are usually in electronics. There's the conduction, convection, radiation, and finally what we call the flow resistance. So an example of all of those are shown here. You've got 2 different boards. Air is flowing between these boards. I won't go through this in detail. I will give you the slides for this. And basically, you've got all those modes present here. You've got conduction, you've got convection, you've got radiation, and finally, you've got flow. So all of these, air comes in at, say, 20 degrees C, will be going out at each shelf maybe at 27 degrees C. And this package is dissipating heat, and it gets picked up as and cooled as the air flows through. So to give you an example that all these modes are available. So the trick is, what is the material property, what is the heat transfer coefficient, and those are the things that we use for analysis. Okay, here are some parameters just to give you an idea. You know, we've got packages each dissipating about a watt sitting on a board, and the spacing between the 2 boards is 1 inch or 25 millimeters. That's this spacing. And the average velocity between those boards is 1 meter per second. It's made of glass epoxy board, I told you, with 1 ounce of copper. And this is a real design. It's 10 watts per meter degree C. It's made of these leads, copper alloy 42, which is 15 watts. The number of leads are 68, and the dimensions. So the design can have package on one side, or it can have packages on the other side. And the manufacturer of the package tells us there's a thermal resistance from the junction inside to the case of 14. So here what we're trying to do is what is the device temperature inside the device, the junction, and what is the board temperature. So you can do the analysis, and typically what happens is here's the package, here's the junction where heat is dissipated. It goes through the case by conduction, goes to the surface. From the surface, it gets carried away by the pins by convection, and on the board by convection. So there are two resistances, a junction to case. This came from the manufacturer. And now our trick is we need to be able to determine what this case to ambient is. If you combine the two, we define what is called a junction to ambient resistance, and this is also a parameter that some manufacturers will give you. So this is normally how we look at an analysis from a design perspective. So this chart just shows you the temperature in the degree C. Depending upon where it is sitting on the board, it tells you the case temperature, the board temperature, and the air temperature. And this is if it's only on one side of the board. Now, if you have components on the both sides of the board, those temperatures will go up. That is because there's less area for carrying the heat out. And typically, what you will find is that if you look at the summary of these results, notice through the case, which is the top, we are losing about, on a single-sided board, 57%. On the board on the back side, you're losing 43%. So what I wanted to point out to you is that typically in most designs where there are only components on one side, both the board and the package equally dissipate heat from the front and the back side. Now, if you put more on the double-sided, obviously there's less board area and most of the heat will go through the package. So these are all well understood. It's been studied for a long time, and we do analysis to determine what the temperatures are inside the junction, and then we do the measurements to follow up with that. Now, the junction to ambient resistance is usually done through measurements and provided by standard testing methods. Typically what they do is they will mount one device on a single test board that is shown here. So the problem with that measurement is that it's not usually has its own limitations. If you did only one device, that its junction temperature is 77. However, let's say you just board temperature, it's 62. Now let's say the board is dissipating in addition 15 watts of power. What happens is that 15 watts of power is going to heat the board up. The junction of the device has gone up to 139. And now if you put a plastic enclosure on top of that to seal that product, look at what happened to the temperature. So the reason I want to point this out to you is when they do the measurements, the device manufacturer usually does it this way. He gives you a data point. However, when we use it, we end up in most cases using it like this, case 3 or case 4. And look at the huge difference in the temperature. You're talking about 80 degrees C versus 140 to 160 degrees C. Now, this, if we took the manufacturer's data and ran with this number, we will be in big trouble. That's why there are limitations. So we do our own measurements, we do our calculations, we use the data, and then we do experiments. Okay. Here are some general rules. Typically, when you've got air cooling inside the equipment for enclosures, the air velocities in natural convection will be in the range of about 0.1 to 0.2 meters per second. When you use fans inside equipment, you will find they will range from 1 to 2.5 meters per second. Pressure losses when you use fans over component will typically be in the range of 2.5 to 7.5 millimeters of water. It's always less than 0.1 to 0.3. It will always be less than 0.5 inches of water. If you use heat exchangers, those are high pressure loss components, and typically they can be in the range of 1 to 3 inches of water. Okay. Now, the heat transfer coefficient for natural convection will be in the range of about 5 to 8 watts per meter squared. Now, if you use fans with a velocity of 4 meters per feet per minute, which is about 2 meters per second, the H will be of the order of about somewhere in the range of about 30 35 watts per meter degree C. So when you have a board that is 8 inches high and there is air flowing around on that board, 8 inches is 200 millimeters, actually the heat transfer coefficient will decrease from the bottom of the board to the top of the board. And most of you who are heat transfer people who have studied fluid and heat transfer can recognize this, because the reason this happens is that boundary layer effect. As you know, at the leading edge, the heat transfer coefficient will be high, and over the trailing edge, it will be low. And so what happens is cooling reduces by about 40% as you go over a 200 millimeter airflow height. And this is important because when you have a reduction of H, you're going to have an increase in temperature. So what you will find in most electronics is that the heat transfer coefficient scales as velocity to the power of 0.7. And this is also something that most of you who are familiar with heat transfer can relate to, because you remember the Reynolds equation, the heat transfer equation, Nusselt is equal to 0.023 Reynolds to the power of 0.7 Prandtl to the power of 1/3. It's exactly what happens in electronics. And what does that tell you? That tells you that the flow inside equipment is always turbulent. Even though your velocity is small, your Reynolds number may say it is only 300. It does not matter. The reason it is always turbulent is because non-uniformities, all the package sizes, they disturb the flow, and the scaling always goes as velocity to the power of 0.7 or Reynolds to the 0.7. So typically the value of H you will get inside equipment will be about 2 to 2.5 that of what you will get by looking at a correlation over a flat plate. And the reason you get that factor of 2 is because of that extra turbulence and mixing that you're getting from flow going over those components. Okay? That's something that I want you to keep in mind, because the reason that is important is, what happens is when you can see all the modes are present, and this becomes a big disturbance, and it creates, some laminar. These things always cause turbulence, and therefore it gives you that extra cooling. So this is actually what we are talking about. This little junction here is the hot spot below the 125 degrees C. Okay, so this package characterization is very important, and remember I told you this is the component 6. It goes from about 8 at 400 feet per minute, which is 2 meters per second, to about 6. 5, roughly 5 at a height of 200 millimeters. This is that 40% reduction because of boundary layer effects that I was talking about. Okay, and here is the data from different test results. You can all see that H scales as velocity to the power of 0.7. You can see all these lines are parallel. Okay, therefore what that means is that flow inside equipment is always turbulent. All right. Let me skip some of these. What I want to do is just show you something about fans. One of the things that we have to deal with is the selection of fans. And as you all know, fans characteristics are provided by the vendor. Usually they have 2 parameters, a flow and a pressure. And depending upon the size of the fan, you can have different curves. So we typically have to select fans based upon the amount of flow we need and the amount of pressure that we can withstand. As I told you before, those come from analysis. So we do CFD analysis. We look at pressure drop over boards, pressure drop over heat exchangers, ducts. All of those are taken into account, and then matching that with the fan curve, and that's how we select the right fan. But ahead of time, we know which one. The thing that I want to point out to you is this particular fan, the large fans. You notice it has this kind of not a monotonically decreasing shape, but something that has this wavy pattern in the middle, and that's a very critical design parameter, because as you can see, if I put different boxes, the system is my box. Where the pressure characteristic of my system meets the fan characteristic, that's my operating point. when I use this product, that's where the product is going to operate. Typically, we want to operate at this point here, about 80% of the maximum flow. This is not good because you're wasting 80% of the flow. This point is something we avoid completely because it's an unstable portion. You can see for a single pressure point, you can have 3 flow points. So the fan actually hunts between these 3. It causes noise, vibration, and failure. So these are things that we take into account. So when we do the CFD analysis, we ensure that we get a design that operates somewhere here because for 3 reasons. This is the point of maximum efficiency, highest flow, and least noise. So all of them go together. So that's the operating point P. Okay. So these are some parameters. I want to give you an idea of the kinds of things that we deal with when we look at using thermal design of electronic equipment. We've got different architectures. We define something that we call a pull and a push, where you've got fans pushing air and these fans pulling air out. These are 2 different designs. Or we have just a push architecture where we push air only to an outlet, or we have a pull architecture only where these fans are missing. So these are different combinations of CAD analysis we do, CFD analysis to determine what the optimum design should be. Now, when we go into selecting heat sinks, you remember what happens when flow goes over bodies. What happens when there's an obstruction? Flow will tend to bypass the obstruction and separate. So if you have a heat sink and on top of a device, if the flow does not go through the heat sink, you're not going to cool it. So look at these 3 designs. This is these 3 points, and notice that in this one, the flow is separated. It is not going over the heat sink. In this one, it is also separated, whereas in this particular design, you notice that all the flow shown by these colored flow vectors are inside the fin. So this is the design you want to choose, because now when the air goes in the fin, it's going to cool the fin. And when the fins get cooled, it's going to cool the device. So these are some additional parameters that you get when you do the CFD analysis, because you can actually see from flow analysis, you can see that you are in fact forcing the flow to go inside the fins, whereas in these, the flow is separating. So CFD is a very, very important and critical tool for our analysis because it gives us extremely good qualitative information, which we then go to through testing, through measurements. Okay, so I'm giving you some references here, useful references. There's heat transfer correlations in electronics. There are 4 correlations that are shown in this chapter. There are a number of others for fins and pins. And then, of course, there are, for sealed boxes, there are other references that are shown here. And finally, there are books as well. There are 3 books that I would recommend: Ellison, Steinberg, and Krauss and Barkhorn. Krauss and Barkhorn is the classic book. It has a lot of theory, and I think from a fundamental point of view, it's the best. Ellison and Steinberg are both practicing engineers. They worked in the defense industry, so they have a lot of practical data. So there's plenty of references today that are available that can help steer you to understand, how to go about it. And in addition, in the United States, several universities have courses on thermal design of electronics. One of them is San Jose State. I know some of the people there, and again, from those of you, if you're from the academic institutions, I'd be very happy to work with you to, help you design a course, because I train people in the U.S. and outside. I've done it all over the world. In fact, I conduct 2-day and 3-day workshop on thermal design and reliability. So I've got a lot of materials to do this for 2 or 3 days. So I'll be happy to discuss these with you if you're interested at a future date. But this is something that, given that India is now moving rapidly into product design, this is an area that I think is become very important. And I feel that engineering students who are graduating with a mechanical engineering degree certainly need to be well versed in the subject, and also as a multidisciplinary course, electrical engineers as well need to understand the implications of thermal design. So I'd be happy to discuss those with any of you if you're interested. So let me stop right there, and if let me stop. I know we've gone over by about maybe 10 minutes or so, but let me stop there and take some questions. So either can you hear me? Yeah.
I can hear you, sir.
Okay.
If nobody has questions, questions can be entered in the chat box, the questions pane. Okay, sir, there seem to be no questions from.
Okay. Yeah. All right. So thank you very much for your attendance. Okay. Thank you,
Thank you,
Sridhar.
Dr. Rajaram,
Okay.
and the recording will be available on the website.
All right. Yep.
Thank
Thanks
you.
very much. Okay. Yeah. Bye-bye.